we will embark on a comprehensive exploration of the Moon's pivotal role in shaping the Earth's history. Prepare for a deep dive into the scientific intricacies of our celestial companion as we unravel the mysteries surrounding its formation, early influence on Earth, and ongoing impact on our planet's dynamics. This journey will take us through the colossal collision that birthed the Moon, cataclysmic lunar events, and the intricate dance between gravitational forces that have sculpted Earth's climate and the conditions conducive to life. Stick around until the end as we aim to present this complex information with the utmost clarity, breaking down intricate concepts into easily digestible nuggets of knowledge. Let's rewind 4.5 billion years. No moon exists yet, but a collision course is set with the planet named Theia. Astrophysicist Jeff Taylor vividly describes Theia's approach, likening it to a growing star, dominating the sky before a blinding impact. The aftermath includes white-hot flashes and earthquakes on the opposite side of the Earth. The massive celestial body known as Theia, boasting a diameter of 4,000 miles, races through space at a speed of 25,000 miles per hour. The imminent collision with Earth results in a cataclysmic impact, unleashing energy equivalent to billions of megaton bombs. This collision triggers the formation of the Moon through a process called accretion, where debris comes together to form a solid mass. Following its violent birth, the Moon gradually distances itself from Earth at a rate of 1.5 inches per year, confirmed in 1969 through laser measurements bounced off a reflective plate left by astronauts. Computational models reveal that the collision between Theia and Earth was a glancing blow, imparting a rotational force. That said, Earth's spin rate higher than the Moon's in the early stages. Earth completes one rotation every 6 hours, while the Moon takes 20 days to orbit. Despite Earth's faster rotation, the Moon's gravitational pull caused a tidal bulge, leading to the Moon's acceleration and eventual drift away from Earth. At its inception, the Moon orbited Earth 15 times closer, exposing it to asteroid impacts that erased 80% of its surface. Approximately 4 billion years ago, the Moon circled Earth at a distance 3 times closer than it does today, significantly amplifying its apparent size. From our planet, this close proximity played a vital role in maintaining Earth's axial tilt, which at 23.5 degrees is responsible for our seasons. The Moon's influence extends beyond stabilizing our axial tilt. It has been instrumental in preventing drastic shifts in Earth's climate and ensuring the conducive conditions necessary for life. Notably, planets like Mars, lacking a stabilizing moon, face potential challenges due to unpredictable axial variations. Examining the Moon's surface reveals a history of intense impacts, resulting in impact craters such as the 700-mile-wide Embrium Basin. About 4 billion years ago, a celestial event involving the gas giants Jupiter and Saturn altered their orbital trajectories, causing a slingshot effect that propelled asteroids towards the inner solar system. This led to a lunar cataclysm, with Earth's gravitational pull steering meteorites and asteroids toward the Moon, marking it as the initial casualty of collateral damage. During this cataclysmic period, some impacts were so colossal that ejected material never returned to the Moon's surface, forming a debris plume. Some of these lunar rocks, remaining a mere 86,000 miles away, eventually entered Earth's atmosphere as intense fireballs, contributing to the geological history of our inner solar system. David Kring's experiment simulating a meteorite impact demonstrated the consequences of lunar cataclysmic events. This period left the Moon with a pockmarked surface, with lunar seas like the Sea of Tranquility formed by molten basalt filling impact craters. Scientists are exploring the potential of Earth rocks reaching the Moon following the discovery of lunar meteorites on Earth. This investigation may provide valuable insights into Earth's past. However, breaking free from Earth's gravity requires an enormous force. For example, the Space Shuttle, needs a whopping 15 million horsepower, while the lunar module requires a more modest 6,300 horsepower to lift off from the moon. Astrophysicist Guillermo Gonzalez debunks the notion that features, like the Arizona meteor crater, can launch material into space. Nevertheless, a colossal impact crater in Mexico might eject some material towards the moon during lunar cataclysms. Impacts on Earth surpass those of dinosaur extinction events, creating holes in the atmosphere. Debris travels to the moon, where the vacuum of space preserves it. The moon, lacking active geology, quickly buries the material, presenting a unique preservation opportunity. Gonzalez estimates that over 1,000 pounds of Earth rocks per square mile may be on the moon, offering valuable insights into the origin of life. While no Earth rocks have been identified on the moon yet, Gonzalez anticipates that future moon missions might reveal them. In the moon's early years, it experienced upheavals and gravitational influence, shaping Earth and contributing to life. 3 billion years ago, as the moon drifted 200,000 miles away, its gravitational impact persisted, influencing oceanic tides on a grand scale. Neil Cummins explores the early moon's significant impact on tides, revealing that they were once 1,000 times higher than current levels. These massive tides, resembling walls of water at 10,000 feet, swept across the land, depositing essential minerals and nutrients into the oceans. The moon-induced tides played a crucial role in creating a turbulent mix known as the primordial soup, where minerals combined and separated. This chaotic environment set the stage for the emergence of the right combination of minerals, laying the foundation for the spark of life. Cummins suggests that the moon's powerful tides may have played a vital role in the evolution of DNA. Some scientists theorize that changes in chemical concentrations during tides contribute to DNA splitting and replicating. Moreover, the moon's tides were pivotal in stabilizing Earth's atmosphere, creating a more favorable environment for the evolution of complex life. Billions of years ago, Earth's rapid rotation resulted in much shorter days, lasting only 6 hours. This accelerated rotation had profound consequences, generating winds and atmospheric vortices, with the intensity of the winds directly correlating with the rotation velocity. In the early, fast-spinning Earth, hurricane-force winds wreak havoc, causing extensive damage. Imagine a scenario where these extreme winds persist, consistently creating a climate dominated by continuous hurricane-force winds and colossal 10,000-foot tides. Such hostility would impede the evolution of life into more intricate forms. Fortunately, the moon intervened, using its gravitational influence to alter our planet's rotation speed. Gradually, this deceleration elongated the day from a brief 6 hours to the now familiar 24 hours, dispelling the norm of hurricane-strength winds. In this newfound peace and calm, more complex lifeforms emerged, establishing the moon as a crucial factor in our existence. Over 3 billion years, the moon continues its journey into space, exerting diminishing influence. Some scientists posit its involvement in earthquakes and volcanic eruptions, while popular belief links the full moon to peculiar human behavior. Presently, the moon orbits Earth at a distance of 250,000 miles, considerably farther than its initial formation. Despite this diminished effect, some still attribute the lunar influence to human behavior. The moon completes its 29-day lunar cycle, causing its appearance to change continually as it orbits the Earth. This changing alignment with the Sun and Earth, as explained by volcanologist Steve O'Mara, plays a crucial role in the lunar cycle. The full moon has long captivated human imagination. Associated with mystery, aggression, and horror, studies indicate that certain animals exhibit behavioral changes during the lunar cycle, with some relying on it for their breeding cycles. The connection between predation and the full moon is explored, suggesting that increased moonlight aids nocturnal hunters in tracking and capturing prey, while the notion of wolves howling more on a full moon is debunked. The idea persists that some mammals, including humans, may become more active or aggressive during this lunar phase. In urban areas like San Francisco, police officers often observe increased activity during full moons. However, scientific evidence regarding the moon's impact on human behavior remains inconclusive. A study in 1976 reported higher crime rates during full moons, and subsequent research noted peak psychiatric hospital admissions during new moons. Despite these findings, recent studies haven't definitively established a link. While cultural beliefs associating full moons with mystical events persist, scientific evidence refutes such claims. Though the moon's influence on human behavior is debatable, some scientists argue that its gravitational force significantly affects Earth. During a new moon, when the sun and moon align, their combined gravitational pull is heightened, potentially stressing the Earth's crust and leading to natural disasters. Volcanologists like Steve and Donna O'Mara use the lunar cycle to predict eruptions, believing that specific points in the moon's orbit can trigger volcanic activity. In 1996, the O'Mara made a significant discovery during an expedition to Costa Rica's Arena volcano, establishing a connection between the moon's position and volcanic eruptions with an impressive 80% accuracy rate. Expanding on this idea, geologist James Birkeland suggests that the moon's gravitational pull could trigger devastating earthquakes. Birkeland carefully monitors the alignment of the sun and moon above fault lines, proposing that the moon's passage might loosen and lubricate these areas, increasing the likelihood of earthquakes. Despite the controversy, Birkeland predictions have proven accurate, as seen in events like the 1989 San Francisco earthquake. Looking forward, concerns arise about the gradual movement of the moon from Earth and its potential impact on seismic activity, with implications for future unpredictable weather patterns. Additionally, the distant fate of Earth and the moon is considered in the context of the sun's eventual expansion, posing long-term threats to both celestial bodies. Until next time, stay curious, keep exploring, and I'll see you in the next video.